Hi, welcome to one of the video on triple five timer. Let us see the objectives of this particular video. So in this video we'll see the simulation of triple five timer as a stable multivibrator, and then first we'll use LTspice for simulating the triple five timer, and we'll analyze the parametric variations of triple five timer stable, and we will see various applications of same triple five timer as stable multivibrator. So let us proceed with the. Okay, we know that this is a circuit diagram of a triple five timer based a stable multivibrator. As you already know, it has got 8 pins, and we are supposed to connect two resistors, two capacitors, so that we can get a desired value of on time, off time. So this is the expected waveform where the capacitor will swing between voltages VTH and VTL, and of course this is the expected waveform. So let us go to LTspice and try to simulate the same thing. So let us go to these components. The triple five timer is there available in this miscellaneous library. Click on that. You got this triple five timer. Okay, this is a triple five timer. You can see usually the pin numbers will not be specified, only the function of the IC will be specified in the simulation tools. Of course, this is pin number 1, 2, 3, 4, 5, 6, 7, 8. So let me take the. Okay, you can just see simultaneously both of them. Now I need to have. Okay, let me just. I need to have two resistors. Let me just take one resistor here, other here, and then I need to have capacitors. Let me just place them here. Let me just name it as CTCS so that I can able to understand their function. And let me name this as CS. Since we named these resistors R1 R2, it's already there. Now let me have a VCC. Let me go here. This voltage. Of course, you can take the battery also, or you can have it as 5 volt. Then let me do the connection. This is now grounded. Let me take a ground also. Yeah, ground here. Of course, the same ground is going here also. Okay. Let me complete the connection and come back. Yeah, now we can see I have rigged up the circuit diagram exactly the way how it is there all here. Of course, here we have written to our convenience different pins, but we have done the connection as per this circuit diagram. So let us try to simulate and try to see whether we are getting the on time, off time as per the desired expression, whatever I have here. So let me simulate it. So for simulation, since it is transient, let me simulate for around 1 millisecond, and let it be 0, then it is 1 microsecond, and done. So let me see the, of course I have placed, you can see now, actually I want to see the capacitor voltage as well as output voltage. So let me just see both this capacitor voltage as well as this. Since the value of R1 R2 is bit high, and since the selected time is not sufficient, it's not, you're unable to see it. Let me slightly extend this time to maybe around 10 milliseconds, and then rerun it. Okay, this is what is the expected waveform. Okay, forget about the first plot. Now we can see the subsequent. Okay, whatever T on T off that we have written over here in this expression, so they are valid for other than the first waveform, first charging discharging. So from here onwards, this is on time, this is off time. You can see the capacitor voltage is charging up to VTH, which is in this case 2/3 of VCC, which is 2 by 3 of 5, which is 3.33, and this is VTL, which is 1/3 of VCC, which may be 1.66. You can actually measure those voltages. So what you can do is you can just take a cursor and then place one here. You can see now it is almost can further zoom it and see what is the voltage there. Almost I can see it is 1.66. It is what is 1/3 of 5. Similarly, you can just go back and try to see what is this voltage, that is maximum voltage. Just move this and then place it here. You can see now it is almost 3.3. So this is 2/3 VCC. So capacitor voltage is swinging between uh, 1/3 and 2/3, okay, as it is mentioned here. So as it is mentioned here, since you connected a stabilizing capacitor, it is going up from 2/3 VCC to 1/3 VCC. So 2/3 VCC is VTH and 1/3 VCC is VTL. Of course, you can measure the on time off time by taking one more cursor. Of course, let me just put the cursors on the output waveform. Okay, now what I'll do is let me just put them on different panes so that you can able to see both of them distinctly. Now this is your on time. Okay, now let me measure the on time off time. Okay, maybe you can just zoom it further. This is my on time. You can see the on time is, okay, forget about this negative sign, it's 1.38 millisecond. Of course, you can verify the for the given values of R1, R2, for the given values of R1, R2 and CT, I want you to verify whether the on time is as per this expression or not. So you can actually find out what is on time here. So on time, measured on time is 1.38 millisecond. So I will leave it to you to verify whether that is exactly as per the expected value or not. You can certainly measure the off time also. How do you measure off time? Let me just measure the off time also. So now off time is from, okay, let me just put it here. This is my off time, almost there. You can see it is now 681 microsecond. This is the off time, which is again as per this expression. As per this expression, you can verify that, okay, whether it is matching or not. Of course, it will certainly match. Okay, this is how you can able to find. Of course, once you know T on T off, you can find the overall time and you can find the frequency of this. This is how you can able to do the simulation of 555 timer using a stable multivibrator using 555 timer. Let us simply vary the value of R1 from, okay, 10K to maybe around 33K. You can see only the on time will increase. If I run it now, you can see the on time, which was 1.38 millisecond, has certainly increased to a larger value. Now this is the on time. You can see on time is almost 2.96 millisecond, whereas the off time, which was somewhere around 600 microsecond, this is of course 690 or 6. You can just further zoom it and see this is almost same as the previous one. So now it's almost there. You can see it is 697 microsecond, which is because you have not changed the value of R2. If you change the value of R2, it will change both off time as well as the total time. Suppose if I make, of course, the on time will also change. Suppose if I make this equal to, of course, those things you can certainly able to verify. And then what we'll actually do is we will actually put a battery here and then try to vary that voltage and then try to see the variation in the what is that the on time. So what I'll do is I will eliminate this. Of course, the time can also be varied by changing the value of CT. Okay, you can just verify that. Let me just show that also. I will minimize this. Okay, this is, let me just make it to 0.2 microsecond. If I run it now, you can see the on time off time will both will change. So I just made it 0.2. Okay, this is how it is looking. Of course, if you want to see it for more number of cycles, you may have to just slightly increase the number of you can increase the time so that you can see more cycles. Of course, if you make it 100 microseconds, sorry, 100 milliseconds, you'll get more and more cycles. And let me again go back to this as around 10K. And okay, let us, what we'll do is first we shall verify the effect of bypassing this diode during the charging time. Let me have a diode here. Let me bypass this diode using, sorry, this resistor during the charging time. So I want to put the orientation of the diode in such a way that while charging it is, the charging is not passing through R2. If I run it now, can you see on time off time are almost same? It's not exactly same because while charging there is a forward resistance involved. While discharging, the forward resistance is not there. It is only 10k here. Here it was 10k plus this RF. So if you want to get exactly 50% duty cycle, you can see it's not exactly 50%. Okay, let me just show you that. Can you see it is still slightly looks lesser? So this is slightly more and this is slightly lesser, even if even the value of R1 and R2 are exactly 10k 10k. This is practically how it happens, because this is not infinite. So this is not that whenever it is reverse bias it is not infinite. When it is forward bias it is not zero. So that's why while charging the resistance is 10k plus RF, while discharging it is the parallel combination of this. So parallel combination of this will be less than 10k, that's why I have a lesser thing. So what I'll do is, let me put a diode, one more diode, so that you can get almost close to 50%. So what I'll do is, I will slightly move this up. Here I will put one more diode in the opposite direction over here. Now you can see while charging it is R1 plus RF, while discharging it is RF plus R2. Now let us simulate and see what happens. Can you see there it's almost looking 50%. Of course you can certainly measure while doing the simulation. This on time is almost equal to off time. So what we have made in this expression here is, this is R1 plus RF, this is R2 plus RF, because this is R2 plus RF is resulting from this diode. R1 plus RF, it is during this diode. This is how you can able to make exactly 50% duty cycle using two resistors of same value, even in a practical case. And of course you can able to eliminate this diode. You can certainly eliminate this diode, and you can certainly get any duty cycle. Usually will not put in practical case, so just to make sure that the effect of this forward resistance, I just included that. So if I run it now, you can see the off time is slightly less compared to on time. So now what you can do is, you can make this as slightly more, maybe 50k. Using this now you can able to get a duty cycle more than, sorry, less than 50%. Now it is, if you run now, you can see off time is so large, on time is very less. So what I do is, let me just slightly simulate for more time. Let me just simulate for more time. You can see now I'm simulating. You can see the off time is so large and on time is so less, because the on resistance is hardly 10k, whereas off it is 50k. That is the R2 is 50k, R1 is only 10k. This is what is the effect of diode here. So we will see the effect of changing the control voltage. Let me just eliminate this, and then of course you can play with this. You can have different values of R1, R2 and all those things. You can get any duty cycle with the presence of diode. Okay, let me also show you, okay, what happens if I put the diode in the reverse direction. Okay, what I'll do, let me just put the diode in the reverse direction. Just take this and then make it control RR twice. It is now placed in the reverse direction. Let us see what happens. I'll run it. You can see while discharging it passes through this, while charging it is the same R1 plus R2. Can you see here? If we can actually make out this, let me just take out. See now, this is on time. Off time is so small. You can see this is off time. This is almost discharging instantaneously. This is discharging very instantaneously, because the discharge time is now decided by only the forward resistance of this diode. This is a forward resistance. That's why when you actually did the experiment in lab, so the LED was looks like it was continuously glowing, but in the actual sense it will be off for a very small duration, which you cannot make out, which our human eye cannot make out this switching off. So that's why it was almost looking like always on. So this is the impact of diode if you are not properly putting the diode. The LED which we actually connected to the output was looking always on, irrespective of this is going off, because this off time is very less. So let me just again go back to the same circuit. Okay, let me eliminate the diode. Let me just show you the impact of changing the control voltage. I will remove this. I'll take off this. Okay, these things are removed. I will put a battery now. Where is battery? It is there again in miscellaneous. So I'll just go to this miscellaneous. I have a battery here. Sorry, this is my battery. I put this here. I will take out the capacitor. Sorry, let me take out the capacitor. Let me make the connection back. Now, as we know that whatever voltage that I put it to control voltage will becomes the threshold voltage, now VTH. Now let me just make it around 4 volts. Now capacitor will charge up to 4 and discharge up to 2, because this VTH is 4, VTL we know that it is half of VTH. Now let me just save this and run. Okay, now if you carefully okay, make both of them in the same plane. See, now this is 2, whereas this would be 4. Can you see here? It's almost 2 volt. This is 4 volts. This is VTH. This is VTL. And of course, we will have a different expression for T on. Of course, we have proved that okay, T off expression remains the same for whatever the supply voltage is, whatever the battery voltage is. So this is your battery voltage. Okay, this is T off. T off remains the same, whereas the T on expression is now equal to R1 plus R2 into CT ln of VCC minus half of V external by, okay, this is VCC minus V external, whereas the T off remains same even if you connect a battery here. So that's what we proved in the class. So that you can verify here. So now let us just measure only the off time here with the control voltage as 4 volts. How much is the off time? So let me just further zoom it so that you can clearly make sure that off time remains same. Oh, sorry, this again came here. Let me take this. Why this is coming? Okay, let me take this. Okay, now you can see the off time is 1.39 millisecond. 1.39 millisecond. Let me go back to my circuit and make this as maybe 3 volts. How much was this? This was 1.39, the off time. Of course, on time will certainly change. So let us just go back and then run it. You can see the off time has slightly reduced because you have reduced the control voltage. Now let me just see what is the off time. This is my off time. Let me remove this pane. Now let me take this. This is my off time. Can you see it's almost 1.39 millisecond? Okay, here I am there. This is 1.39 millisecond, almost. You are there at 1.39 millisecond. That's why the expression for the off time will not change. So off time remains as 0.69 RTCT in spite of having a supply here, in spite of having a battery. Even if you have a battery here, so the off time expression remains same, whereas on time will only change. Okay, now the major application of such type of putting a voltage source is the total time of this 555 timer output will change with respect to the control voltage. If you keep on varying this, the total time which is also affecting the frequency. We call it as voltage controlled oscillator. Let me just find out what is the total time here. So let me just zoom this and then make the time here full time. Okay, this is my full time. You can see it is 3.62 millisecond for 3 volt. So what I can do is time is equal to 3.62 millisecond for a V external of 3 volt. If you change the V external to some other voltage, maybe 4, and if you rerun it again, again measure the total time, that is on plus off. If you measure the on plus off time, earlier it was a 3.62 millisecond, now we can see it has moved to 5.79. So this is with equal to 4. So time has now become 5.79 millisecond. Let me just show you this, what we are trying to do. You can see once you change the V external from 3 to 4, the total time has actually increased from 3.62 to 5.79 millisecond. That is, as you increase the voltage, the frequency reduces. This we call it as voltage controlled oscillator. Okay, keeping this in mind, let us do one more application. Instead of applying a DC voltage, let us apply a sine wave and see what happens to this. So for that, okay, let me just consider a bit smaller resistance here. Maybe you can make it as 1K. This is also, maybe make it as 1K. So let us try to have a 50% duty cycle, meaning that, okay, let me have one diode here, let me have one more diode here, so that it looks like a 50% duty cycle in general. I am just using two diodes here so that it is exactly 50% with values of R1. Okay, let me make this also 0.1 microsecond. If I run it now, okay, let me make this also equal to, okay, this is 3.33. Let me make it 3.33 because 3.33 will be the voltage under a normal condition, that is without any control voltage, without any change in the control voltage, that is without any external supply. You can see this is looking like exactly 50% duty cycle. So you'll get similar type of waveform even if you don't connect this. Okay, let me just disconnect this and show you that. I will take out this, and if I run it, it's the same waveform. Hardly there is no change. So it's exactly 50% duty cycle. You can see on time equal to off time. Now, what was the voltage here? It is 3.33. That's the voltage that you'll be getting here. So of course that you can check here. Okay, let me show you that. See now, what is the voltage here? It is 3.33. This is what is 2/3 of VCC. 2/3 of VCC. Since VCC is 5, 2/3 of 5 is 3.33. If I make that VCC as 15, if I run it now, that will be, the control voltage will be what is that, 10 volt. 2/3 of 15 is 10. That's what you're seeing here. So this is 10 volt. The control voltage is 10 volt because this is 15. But you can see here, so the on time off time remains exactly same because T on T off are independent of the supply voltage. Let me again make this equal to 5. Okay, let me just rerun it, and let us apply a sine wave here. Let me apply a sine wave. So if I apply a sine wave here, so what I do is, okay, this is okay. Let me just copy this. How do I copy? This is copying this and then place it here. Let me change this to advanced. This is sine wave of offset 3.33 volt, and you apply a 1 volt amplitude This is a frequency of maybe make it as around 100 Hertz. That's fine. Now if I apply now, I will save it and run. See now, can you see the width of the pulse is keep. Okay, let me just show you only that waveform. I will take out this capacitor voltage and this voltage also. Can you see here? Okay, let me change the scale of this also. How do I change the scale? Okay, okay, instead of 5, let me make it 6. Instead of bottom 0, let me make it -2. So that now we can see. Can you see it? Is the width of your pulse keep on changing? It is more here, it is less here. So if I superimpose this input waveform, let me just take that. Let me superimpose this. See now? Let me again change the scale now so that it is properly 6 and -1. This is interesting. See now, when the input when the control voltage is in the positive half, the width of the on time is more. So over here the on time is left. Whereas if you can measure the off time is same during the entire cycle. During the entire output, the off time remains same, whereas the on time is keep on changing. You can see the on time is width is increasing. Of course, this is keep on increasing here, and then it is keep on reducing. So since there is a width variation, we call such type of waveform as pulse width modulated waveform. So next, okay, what we are, one of the major application of 555 timer is PWM generation. So what is this? Is pulse width modulated waveform. So there is a pulse width which is being changed as per my signal here. So this is a sine wave here, this is a sine wave. So as the sine wave amplitude is keep on increasing, width is increasing. As the sine wave amplitude is keep on reducing, the width is reducing. So that's why there is a width variation happening depending on the message, depending on the depending on the sine wave. Only constraint is that this sine wave should have some DC shift. This should have some DC shift, and this should not go below 0. This should not go below 0, and this has to have a bit lower frequency. Meaning, suppose if you are having the 50% duty cycle pulses like this, my input frequency should be something like this. Meaning, in one cycle of my control voltage, I have to have at least 10 to 15 such pulses. Suppose if this is 1 kilohertz is your frequency, then this should be 100 hertz, so that you can able to see there is a width variation at least in 10 pulses. Suppose if the frequency of this also becomes 1k, you can see the the variation of amplitude happening here itself. You cannot see the width variation in only one cycle. If you want to see the width variation, the frequency of the control voltage should be far less compared to the oscillating frequency. Let me just demonstrate that also here. Let me just go back and increase the frequency of this from 100 Hz to a different value. Let me just show you that. See, now it is 100 Hz. If I make it 1k, you can see what happens. See now, you cannot see much of width variation. Of course, width variation is there, but you're not seeing too many pulses. Suppose if the frequency is further more increased to maybe around 5 kilohertz. Suppose if you make it equal to 5 kilohertz, I am not getting the width variation because I'm not getting the width variation. What is required is this sine wave should have larger time compared to the square wave. So that's why, as it is shown here, this control voltage, the voltage that is applied to pin number 5, should have a low frequency. Of course, along with that, it has to have some DC shift. So you can see, suppose the DC shift is not there. Let me just go back to this and then try to do the same settings now. I'll do the same settings. You can see now it is okay. Let me just go back to this, and then okay, now this is fine. If I run it, now everything is fine. You can see there's a bit variation. Suppose if I take out the DC shift, how do I take out the DC shift? Let me just go here and then make this 0. If I make it 0, if I run it, you'll not get a proper pulse. You'll not get a proper pulse. You can see now this is the type of waveform you have. See, this is your sine wave. Even though it is frequency is low, since you are not DC shifted, you are not getting a PWM, because the voltage at this control voltage is negative and it is very less, so that's why you're not getting the pulse at all. So that's why we need to have this, should have some DC shift. It need not be 3.33. even if you give a shift of 2 volts also, it is fine. See, now you're losing some pulses. Make sure that this is slightly further more increase. If you further increase means okay, you need to increase the DC shift to around 3 volts. You can see now you're getting it. So this way you can able to see all these variations. So what we have seen is, we have seen the simulation of amplifier timer, and we found out the on time off time duty cycle can be changed, and we have seen how it can be used as a voltage controlled oscillator and how it can be used for pulse width modulation. Voltage controlled oscillator is this: as you change the voltage, this frequency is changing, this time is changing. When I say voltage, it is this control voltage, it's not this VCC. If you change this VCC, no change in the frequency. If you change this voltage, control voltage, then only the frequency changes. That's why it is called as VCO. Instead of a DC, if you apply a sine wave, something like this, with some DC shift with low frequency, you'll get pulse width modulated signal. Okay, that's it for the day.